You ever wonder how a website finds exactly what you're looking for pretty much before you've even finished typing? I mean, it feels like actual magic, right? But behind that blink and you miss it result is this fascinating process of pure logic and just incredible speed. So today, we're going to pull back the curtain on how databases actually think. Think about it. You're searching for a product, you're filtering your photos, you're looking up a friend's contact info, and bam, the result is just there. So how in the world does a system sift through potentially billions of pieces of information to find your one specific thing that fast? Well, that incredible speed. It isn't just about raw power. It's about a very, very smart split-second decision. See, every single time you hit search, you're kicking off this chain of events that is designed for one thing and one thing only: absolute efficiency. Now, in the tech world, your search is called a query. That's all it is, a formal question, usually written in a language like SQL, that you're asking the database. It's basically just a structured way of saying, hey, find me all the users from London, or show me all the products under $50. And here is where things get really smart. A database doesn't just blindly start searching. No, its very first job is to analyze your question and figure out the absolute fastest, most efficient path to the answer. It's not just about finding the data, it's about finding it intelligently. Okay, the absolute best way to picture this is with an analogy. I want you to imagine the database is this massive, city-sized library. The database system itself, well, that's your personal super-librarian who knows this library inside and out with one single goal: get you what you need instantly. And our librarian, they've got a 3-step workflow. First up, parsing. They check your request to make sure it even makes sense. Does that book or author even exist? Second, optimization. This is the real genius part. The librarian plans the most efficient route through the entire library, making sure they don't waste a single step. And finally, execution. They follow that perfect path and go grab the info. This optimization step is everything. Seriously, the goal is always to reduce the cost. And by cost, I mean the time, the memory, the processing power required to get the job done. A great librarian, just like a great database, saves precious resources. And that saving is what makes everything feel so incredibly fast to you. Here's a perfect example of how that librarian thinks. You might ask for students older than 20 and younger than 30. But our librarian knows it's way more efficient to search for those between 21 and 29. It seems like a really subtle rewrite, right? But when you're dealing with millions of records, these tiny little changes save massive amounts of time. Our librarian has a whole toolbox of tricks. They use an index, which is literally like an old-school card catalog, to avoid having to read every single book on every shelf. They figure out the smartest way to combine info from different sections, and they make sure they never do any redundant work. And, crucially, they only grab the specific info you asked for. They're not going to bring you the whole encyclopedia when all you wanted was a single paragraph. Okay, so this is all great, but it kind of begs a fundamental question, right? How does the librarian even know where to look in the first place? For any of these tricks to actually work, the library itself has to be built on this foundation of impeccable logic and order. And that foundation, it's built on a really strict set of rules for keeping all the data tidy. In the database world, we call these rules functional dependencies, and they are the secret grammar that makes this entire system work so beautifully. Think of a functional dependency as the library's golden rule. One piece of information has to uniquely determine another. So for example, a book's official ISBN number should lead you to one and only one title. There's zero ambiguity. In this case, the ISBN is the determinant because it determines the dependent value, the book's title. This relationship is written with a simple arrow. X determines Y. And this isn't just some fancy notation, it's a promise. It's the absolute bedrock of database design, and it guarantees that if you give the system X, it will always, every single time, give you back the same Y. Let's make this super real for a second. The rule here is simple. A student ID determines a student's name. If you look up ID 102, you will always get John Smith. You will never, ever get Priya Kumar. This unbreakable guarantee is what we call data integrity, and it's absolutely essential for preventing total chaos. So what happens when these rules are broken? Well, you get a data mess, a completely disorganized library where our super-librarian gets confused, and finding anything becomes a nightmare of errors and painfully slow performance. Now, data usually gets messy in a couple of ways. You can have a transitive dependency, where information is linked indirectly through a sort of middleman. Think your student ID leads you to a department ID, which then leads you to the department's name. It's an inefficient chain that can break really easily. The other mess is a partial dependency, where a piece of info depends on only part of the main identifier, which is kind of like filing a book under just the author's first name. It's incomplete and super confusing. Let's look at a concrete example of this mess in action. In a single orders table, the order ID might determine the customer's name, and then the customer's name determines their address. That's a classic transitive dependency. So what's the big deal? Well, if that customer moves, you have to find and update their address on every single past order they've ever made. If you miss just one, you now have conflicting information, a major inconsistency. The solution to this mess is a process called normalization. It's basically just tidying up the library shelves. You break that one big, messy table into two clean, focused ones. One table just for customers and their addresses, and another just for orders. Now, a customer's address only exists in one single place. It's consistent, it's efficient, and it is so much simpler to update. So let's tie this all together. What we've really been talking about here is that the incredible speed of modern databases isn't just about faster hardware. At its absolute core, it is about a deep, fundamental commitment to organization. This whole journey starts with those strict rules, our functional dependencies, that define how data is supposed to relate. Those rules let us build a beautifully organized library through normalization. That clean structure that empowers our super-librarian, the query optimizer, to find the perfect path every time. And the end result of all that amazing work backstage is the split-second result that we all just take for granted. And really, it all just boils down to this: the speed, the reliability, that feeling of magic. It all begins with understanding this one core principle. You just can't have an effective database without building it on the foundation of these simple, powerful rules. So, I'll leave you with this to think about. We've just seen how the hidden architecture of data makes a simple search possible. And it really makes you wonder, what other invisible rules and organizational systems are quietly shaping the rest of our digital world, from our social feeds to our streaming recommendations?